Cool. Well, hi, everyone. I'm happy to introduce to you Su-Lin Liu. We had a great conversation a couple of weeks ago. And he's, fortunately for us, he's agreed to give us this talk. Su-Lin has a PhD from Princeton and a postdoc at MIT and various other things. But the thing that I find the coolest is he worked as a research engineer for a while, just like me. He's done work in material science, 3D scene reconstruction, but today we're talking about diffusion for NLP. So with that, take it away.
Yeah, thanks so much for the introduction and thanks for the invite. Nice to meet you, everyone. My name is Su-Lin. So you can pronounce as a longer Su with Lin. So fun fact, there's a famous people I shared the same name with. Su-Lin is also the name of the first panda that was brought to the United States back in a long time ago. Yeah, so a little bit about my background. So I grew up in China, went to undergrad in Singapore and majored in electrical engineering, and then worked for 2 years. Then came to the United States to do a PhD. So my PhD mostly focused on machine learning methodology. Currently, I'm doing a postdoc at MIT. So in this talk, I will basically talk about one of my recent work about discrete diffusion. So how to do planning in discrete diffusion. It's a recent paper accepted at ACLEAR this year. So diffusion models, I bet most people are quite familiar with the idea. So the idea is like you corrupt the same image with different amount of noise, and then you try to use the neural network to learn to revert from any intermediate point of this noisy image back to the original image. So so essentially what you're learning is like from any intermediate point, what's the average direction to learn to denoise back to the actual real images. So discrete diffusion is this efforts that people try to apply the same idea but for discrete objects, mostly for sequence data. So the first type of discrete diffusion, people call it masking diffusion or diffusion with absorbing state. So the idea is very simple. You define a mask token, which is here to be this kind of tokens, and basically the noise distribution is just basically this absorbing state that is a mask token. So the corruption process is to apply the mask tokens to the original data in some random ordering, and when you try to learn to denoise, you're learning to denoise the mask tokens in the random ordering as well. So this is called masking diffusion. So it's very related to mass language models. Basically, sometimes previous mass language models only talk about denoise from some portion of mask tokens, but in this case we're trying to denoise from a full sequence of mask tokens, and in some random ordering denoise one by one, or under the framework of diffusion you can define a bigger time step that you can actually try to denoise multiple tokens at one time, even though our current neural network architectures do not allow us to model this kind of joint distribution in a very efficient manner. So the most accurate denoise you can do is still token by token. So very related to autoregressive models, if you consider you are just generating a sequence of a fixed length and you're trying to denoise in a certain ordering, in this case from the first token to the second one. So it's a pretty general framework, I would say, for discrete diffusion. So the other type of noise distribution that is more analogous to the actual diffusion models for image data is basically assuming there's a random noisy distribution. So in this case, instead of defining extra mask tokens, we basically define the noise distribution to be uniform random across all tokens. So in this case, we're doing this character level language modeling. The starting noise distribution will be a random very random distribution. So we sample random tokens, and then we try to denoise the noisy tokens in some kind of random ordering, one by one, and hopefully after some amount of steps, we denoise most of the tokens. So here are like two possible routes from starting from the same set of random tokens, a sequence of random tokens, but our model can denoise based on which tokens they want to denoise first, and then at some stage there are like on the left I'm showing that some cases you're trying to denoise but you're not always successful, and then the final sequence still contains a random token, which is different from the mask token. So in the mask token case, you denoise every mask token, there will be always like tokens, but in this case, some noise tokens remain in the data. In the other case, we got lucky, and in the final step, the denoising happens to be correct for both of the tokens that are noisy, and then we achieve the good reconstruction or denoising. So I've talked about these two different ways you can define this noise distribution, and which one should we actually use for discrete diffusion, especially for languages. So as we see in the mass diffusion, the limitation is pretty clear. Like it's every token, once m mask cannot be changed. I guess this is also like a bottleneck for autoregressive models, but as pointed out by Sander Diamond in his tweet, this is apparently like a limitation of mass diffusion, that you cannot change the token once it's denoised. So uniform diffusion seems to be more flexible because we don't assume any token that is denoised is a clean token. So that gave us the more chances of denoise the tokens again if we make some mistakes or the tokens are not finalized yet. However, in reality, mass diffusion always works better. So that's starting from like the very seminal work of applying the idea of discrete diffusion, but to like all the recent work only focusing on training mass diffusion models for language data. So the hypothesis, like my hypothesis here, is like it's always easier to learn to denoise with these mass tokens, because if you have noisy tokens, then the learning task is more complicated. You have to learn which tokens are noisy and then focus on learning those tokens to be denoised. So yeah, there are more recent like efforts in scaling up these diffusion language models. Some of the first work, I believe, trained the model up to like 7 billion parameters in the Llama architecture. The second is a recent startup trying to build the first commercial available diffusion language models. So in my work, I will not talk about those kind of scaling, but more talk about from a methodology point of view, how do we achieve the true iterative refinement style generation with discrete diffusion? And in particular, the idea, the method is pretty straightforward. So I will first explain how this idea, this planned denoising works. So we assume we start from some noisy distribution instead of a mass diffusion distribution. So in this case, in the intermediate step of denoising, we look at this partially denoised sequence, and we use first take this sequence into a planner and do a self critic on which tokens are thought to be more noisy than others. So in this case, among all the possible data we can denoise this token, this sequence into, there's more chance of the last 3 tokens being noisy compared to the first ones, because the first 2 there are many possible words that are made up of the first 2 tokens compared to the last 3. So based on this probability for each token, there's a probability of the token being noisy. We can pick which token to denoise proportional to this probability. So let's say we randomly sample according to this probability. We pick the 3rd token to denoise, and then we will pass this information to a denoiser to denoise. So the denoiser just focus on denoising for this token, and in this case we denoise it to a letter E because there's more, a lot of the case BR follows with E or something like that. And then we do this iteratively. So what we are doing here is that our time progress of the diffusion will also be always recalibrated based on the planner. So as long as the planner thinks there are some noisy tokens remaining, we will recalibrate the time to be some time according to how much of the sequence is clean. So we continue this process until everything is regarded to be clean tokens without noise, and then we stop the sampling. So that's how the method works. Next, I will give you a very simple justification of why this should work. So before going to that, I will first give you a brief idea of what's diffusion learning, what are the diffusion models learning. So for continuous data, we are learning this ODE that is transporting the distribution from the noise distribution to data distribution. So what we're trying to learn are those vector fields that transport, if we are in this middle part of a partially noisy data, we're learning the direction of where we want to move the data towards to. So the neural network is learning this vector field. So similarly for discrete data, we are learning this generation rate matrix. So it's a rate of how we want to move our current data towards to. So for each dimension of the data, so D here means that this dimension of the data. So for that dimension to move to a different new token, you can show that it basically for mass diffusion, it depends on the first term, which is basically a noise removal rate based on how much close you are towards the final of the diffusion process. So if you're very close to the end, means your T is close to 1, this rate will be extremely large because you have very little time remaining to make the thing happen. So you have to make it happen fast. And the second part is basically indicator function of indicating whether the current token is noise or not. So if it's a mass token, it means we still need to denoise that. If it's not a mass token, we're not denoising that. And the last part is this probability of denoising, which is basically, if we are denoising this token, what is probability of denoising it to a new token JD? So similarly for uniform diffusion, although we don't have a notion of this token being noise or not, but we can do a similar decomposition by having this Bayes rule, and for this holistic generation probability, we actually can decompose into a probability of this token being noisy, and then if this token is noisy, what should we change it next to? Because if this token is not noisy, there will be a 0 probability of changing this token to any other token. So based on this observation, what we can do is we can actually model these two parts separately, and then do this sampling, which is we continue this iterative process, and in every sampling step, we simulate the delta T until the next state transition. So there's for each dimension there is a generation rate for different dimensions, but we're just gonna sample the delta T until any dimension that encounters a state transition. And then the sampling, basically you can do ancestral sampling by first sample according to the noisiness of the different dimensions. So apparently the dimension with a higher probability of being noisy should be sampled more frequently, because it's faster for those tokens to be actually changed to a different value. And then after getting this planning, which is basically pick the position to denoise, we can use the denoiser and denoise the chosen position. So here is just a very concrete example of what the planner is predicting and what the denoiser is doing. So it's initially, since we assume there's no natural ordering of denoising, so every token based on the planner's prediction, every token is noisy, and then we will draw a dimension based on this probability. So in this case, it will be a second token, and then we try to denoise using the denoiser, and then we, change the token value to whatever the denoiser thinks should be the value to fill in, and then we continue this process. So you can see that different times, the more the cleaner tokens are less likely to be chosen because we have more noisy tokens we need to denoise. But also we can see that sometimes we make mistakes in the denoising, like in this case. We're trying to denoise the last token, but we don't have a good sense of denoising it. So we denoise it to a token that is not making sense. So the actual time progress, we will always not assume we travel the same amount of time we expect to travel, but recalibrate the time back to whatever we think the current state is. So this allows us to continue denoising and choosing the next token to denoise until the whole time reaches 1. But instead of our expected original schedule reaches 1. So this allows us to use as many steps as we need if the current state of all the tokens are not clean, which means the probability is not 0. So here's a animation made by someone else who want to study how this method works, but it's very simple MNIST data generation task. So in this case, the planner prediction in the very beginning, you can see everything is white, which means everything is thought to be noisy because we have pretty much every pixel to be noise here. And then we can see after filling in some of the background with black pixels, the planner thinks those are correct, and so those are not noisy. And we can see more and more more tokens are less noisy than others. And in the final generation, we can see it's pretty confident that some tokens remain to be noisy, which are the backgrounds that are not blacked out yet. So this basically is a example of the actual thing happening in the sampling process. So for training, you might wonder how do we train this planner? So it turns out to be pretty simple. You can corrupt original data with random tokens, and now you have labels for which ones are clean and which ones are noisy. So to train this planner, I also call it self-critic, which is basically critic on yourself which part is noisy. So you can just minimize the cross entropy. And for the denoiser, you can do whatever the original discrete diffusion denoiser training does, which is basically try to recover the noisy tokens to be clean tokens. So it turns out the actual elbow of the diffusion process also just decompose naturally to these two parts. So what do you think is the most intuitive way to train is actually also theoretically principled. So in our paper, we also show that you can train reuse a mask denoiser. So in this case, the denoiser takes in what tokens you think are noise and apply the mask to it, and then you can try to learn to denoise by filling in the noisy tokens with mask tokens, because according to previous experiments, seems like mask denoiser is faster to train, or at least it's more efficient to train a mask denoiser. And also many of the pre-trained denoisers are of this type. And then we show that you can actually combine a planner trained on this type of corrupted data, but also use a mask denoiser for denoising. So the last final way you can do this is by training a holistic reconstructor, by just learning to reconstruct from a partially corrupted sequence. Although this thing is very slow to train because the task is significantly more complicated. But after training this to good quality, you can actually decompose this problem to two parts, and then use the first part as the planner probability and the second part as denoiser. So those are the three types of ways you can do this sampling, but with different ways of training the planner and the denoiser. So what's different here of the plan-and-denoise sampling. So compared to the reconstructor or denoiser-only method, the first difference is that we simulate the delta t until the next state transition, which is very different from like previous works that assume equal delta t. I guess like equal delta t makes sense for the continuous data because everything is changing constantly all the time. But for discrete data, we actually shouldn't waste the delta t if there's no state transition happening. So that's why we propose to simulate the delta t until the next state transition. But more importantly, it's about this planning, that train this self-critic, look at the current generation and pick on which ones to denoise next or again. So at least like it introduced one-step planning for each of the generations. So, but it also works as a self-verifier until you sample until everything is correct. So for the denoising, like one thing I observe is that if your denoiser needs a time information for denoising, such as you are denoising using I guess for mass denoiser, you don't actually need the time information, but for other denoisers, like when you are denoising from partially corrupted sequence, the time information is very crucial there. So if you recalibrate the time based on the estimate of the current time by the planner, it always gives you a better performance as by providing better context for generation. So the resulting behavior is this kind of agentic iterative refinement that happens until everything looks good to the planner. So first we do this on the very simple task, which is text 8 character level language modeling. So in this case, every model is overtrained. So the discrete diffusion is overtrained, I think, much more than the autoregressive model. So if you overtrain autoregressive model, they turn out to be like regress on the performance. So we only train them until like to some decent amount of tokens. So the main idea, the main takeaway is that first of all, you can apply this random remasking to the generation. Like you can, like when you do discrete diffusion, you can randomly reapply the mask to part of the tokens and then denoise those again. So that corresponds to this method with eta equals to 15. So in those cases, it turns out to give you a better performance in terms of this negative log likelihood, which is a generative perplexity measured by a larger language model versus this entropy measured on the generation sequences. But with the planning and denoise, you can actually have a more principled or targeted re-denoising of the tokens that you have generated. So that gives you a much larger boost in terms of performance. So we compare like different ways you combine the planner with denoiser. So in this case, if you actually get the holistic reconstructor trained properly for a long time, it gives you the best performance. If you just combine the planner with a mass denoiser, it actually gives you a pretty good performance trade-off if you want to reuse any of the pre-trained denoiser. So here we try to think about which method is most token efficient for training if we don't have that enough budget for training. So it turns out if you train the planner and the mass denoiser separately, so in this case every model is only trained for 20K iterations. By combining this planner with a mass denoiser gives you the performance that matches those performance that are overtrained for the mass diffusion models with the random remasking. So this really shows that training separately for doing this self-critic planner and denoising separately gives you a large, really large performance gap between simply only training a single denoiser or a holistic denoiser. Yeah. So here we study if we increase the number of sampling steps, we can see this iterative refinement behavior. So basically, if we only allow for the sequence length is 256, so if we only allow 256 number of steps of denoising, our model does not perform any better than other models that are using same number of steps. But if we increase the number of steps from 256 to 512 and then 768, we see more and more improvements. So that means this method is able to use test time compute because we have a planner for targeting which tokens remain noisy and needs to be corrected. But also it shows that when you further increase the number of steps, it doesn't cause the performance to diverge because we always only try to re-denoise the tokens that are noisy. So next we do this on the larger scale experiment. So it's on the OpenWebText with GPT-2 scale models. So compared to discrete diffusion models like said, small, we achieve a significant performance boost by combining a planner with a denoiser. So here we use a small planner and a small denoiser, and then you can see that the performance, it gets much closer to autoregressive models, but although it doesn't really close the gap, it's completely. So we want to be fair. So we also compare, the medium-sized denoiser, which is of 20 million parameters, compared to a small denoiser plus a small planner. So again, you can see by splitting compute between the planner and the denoiser, or at least have this plan and sample strategies more significantly important than just scaling up the denoiser size. We also apply this to ImageNet token generation. So in this case, we do like a VQVE type tokenizer that tokenize the image into discrete tokens, and then we do the same experiments. So first of all, we find the average denoising accuracy here is much lower than text. So after training, for the mass denoiser for this rough number of tokens, we observe that the accuracy is much lower compared to the OpenWebText or text8. So one of the potential reasons is it's undertrained denoiser. The other is also because the tokenizer is pretty small, so that means your tokens distributions are maybe harder to learn compared to those language tokens for denoising. So the main so we compared mass diffusion, maskit, which is a greedy way of picking which token to denoise next based on denoiser's confidence. So it's like you don't actually denoise in random ordering, but picking next token to denoise based on which token the denoiser is most confident about. So that means this will ensure you have a higher accuracy in denoising because you're only trying to be confident in denoising. But you lose this diversity in sampling because of this greedy selection. So as you can see that if we do random denoising, like using original mass diffusion, the performance is really very bad if we don't do any logic annealing. So that shows, the denoising accuracy really hurts. And once you denoise, you cannot you cannot correct the previous mistake. So this make the image look really bad. The maskit works really well, but you can also see that the greedy selection causes diversity to harm diversity. So the FID score becomes worse if you have more number of steps, because more number of steps meaning you're denoising one token at a time. The total number of tokens is 128 here. So if we denoise in 8 steps, we are doing parallel decoding. In comparison, the plan and denoise sampler allows us to use this low quality denoiser, but after doing this iterative refinement, we can get images that are of good quality and diversity. So, but with logic tempering, if we use a logic temperature annealing, the mass diffusion works just okay. in this case. And now you can see the mask kit starts to perform worse because although the quality is still good, the diversity is further harmed by this logit temperature annealing. So here are the images generated. So this is our method. This is mask diffusion with random ordering. This mask kit with greedy ordering by picking the next token that is most confident about. You can see the difference of the diversity of the generations. So here is without logit annealing. And here is another image. So basically, our method, by increasing the number of steps, you can see much of the image is untouched, except like some of the aesthetics are further improved. So that shows, what the method is doing is like picking on whichever tokens are still remain to be like imperfect and trying to refine those. Cool. So here is a summary of the method. So our sampler explicitly introduces planning into the generation process. So this leads to simplified learning task. So we can, learn the planner and denoiser separately and also at the same time. So this allows you to reuse the whatever test time compute you have available to do iterative recalibration or refinement instead of having this compound sampling errors in the mass diffusion regime. And also, the generation process here is inherently agentic because of the way you can decompose the generation into this latent model decomposition. The limitation here is we haven't really done offline training. We'll only do offline training here, so we haven't done online training. So that means if your generation trajectory diverge from whatever your training distribution look like, then the planner may have robustness issues. So that's a potential limitation. So the question is will diffusion language models be the next pre-training method since we are running out of pre-training data? So I will share some of my insights or thoughts about this. So recently there has been a lot of efforts in improving discrete diffusion mostly from the academia world. So one theme is by combining autoregressive models with diffusion language models. So one path is by continue train from autoregressive models. So training a mass diffusion model from diffusion language model from scratch is pretty expensive because you have to learn denoise in so many different orderings. But if you take a autoregressive model and continue train from that, that seems to be much more affordable, at least in an academic setting. The other way is by combining the idea of autoregressive sampling and diffusion in sampling. So this block diffusion paper tries to sample a sequence block by block autoregressively. So when sample each block, you're trying to do this diffusion language model sampling that allows you to maybe sample in faster speed by doing parallel sampling. Is there a question or? Okay. At the same time, there has been more and more of using planning for discrete diffusion. So there's a popular heuristic for error correction, which is basically based on your generator's confidence prediction of all the tokens. You remask those tokens that are thought to be low confidence by the denoiser, and then re-denoise them again. So our work actually provides why this actually works. So this always has been a heuristic, but in my work, turns out when you do this generation and you thought about it in the uniform random noise denoising perspective, there is this heuristic that you can pick whatever is most noisy and then denoise them. Okay. So in my view, I think discrete diffusion models are not going to replace the language model anytime soon, but the idea is pretty relevant to the current language models. So first of all, I think it's a very useful framework for thinking about how to generate synthetic data or data augmentation. So the previous way of training is by always doing passive learning. We just try to predict next token based on whatever high quality data we have or whatever data we have. But we can be more active in collecting data. So discrete diffusion basically is about predicting different parts of the data. So that's relevant to the fill in the middle like prediction strategy for training language models. But also it can give you data about like predicting which parts are corrupted. So it can make the model better at self-reflection or use it as a judge. The more interesting perspective is about how can you generate this kind of synthetic reasoning trajectory from the discrete diffusion process. So imagine you have the final answer as the clean data you have for solving some task. You can always perturb this clean data with some noisy distribution, and then compare, the change between the two, and generate, the thinking process of, what's changed between these steps. So now you can have a long trajectory of this reverse trajectory of like how do you iteratively get closer to the final answer. The other direction I thought is pretty interesting for discrete diffusion is like how do we use this idea for faster parallel decoding. So from my experiments, I find it's much easier to fill in tokens or autocomplete some tokens in like one forward pass if you are at the later stage of the generation. So imagine in the image case, once you have filled in 50% of the image, you can pretty much fill in the rest by looking at the context and fill in. So how do we actually make use of this property in generation and use and make the current language models incapable of predicting multiple tokens in one forward pass? So the assumption here is like the tokens are either needs to be independent for generation or they are deterministic. So the current models, like we use transformers, so they're only learning the conditional distribution for each of the token. But if all the tokens are independent distributions, so the the independent conditional distribution multiply each other becomes a joint distribution. Or if the token like are deterministic, so you can predict multiple tokens in one shot because everything is deterministic. So that's all for the presentation. Thanks very much again. And yeah, if you have any questions, happy to discuss in more details.
Yeah, I have a question. So you had that trick where the denoiser is allowed to sort of reset time by a little bit, right?
Yeah.
That mean that you have unbounded compute potentially if it just keeps resetting it all the time?
Exactly. Yeah.
So how do you prevent that? We got to get done at some point.
Yeah. So so the criteria for stopping here is like if every probability of noisy is less than a very small number in my experiments. And in practice, for all the experiments I did, like the text8 and OpenWebText, I use up to 4x number of some denoising steps as opposed to the original sequence length, and that seems to be like just more than enough for sampling. But in a case where you're not making progress, I guess this is causing you problems. But it's also causing problems for other methods, which the denoiser is not capable of, just improving the sequence further. Yeah.
A different question is the denoiser and the planner, are they basically the same network, the same architecture?
Yeah, I just reuse the same architecture. Yeah, they're also often of the same size as well. Yeah. But it's much faster to train a planner, like the loss converge much faster. You don't need that much number of tokens as opposed to training the denoiser. Yeah.
Is it true that at inference time, if you have a good planner, you don't need to run the denoiser that much because there's far fewer tokens to predict?
Sorry, say that again. Like if you have a good planner,
you don't need to run the denoiser on tokens or with tokens that are already known to be be good? I guess there's some inference time benefit where it can run faster.
So I'm thinking like for denoiser, right? If there are 5 number of noisy tokens here, so you still need at least 5 number of steps if you're only denoising 1 token at a time. So I don't think you can, even if your planner is super good, it's only good at verifying which token is correct and which token is not correct. But if you do like faster parallel decoding, like not decoding 1 token but multiple tokens at a time, and if the planner is very good, then potentially you can use this to have like less number of denoising steps. Yeah, but with the like parallel decoding framework. Yeah.
Yeah, I guess there's benefit to having fewer steps, but there's never a benefit to, like, denoising 1 token takes the same time as denoising all the tokens.
Exactly. Yeah.
Okay.
It's just like a significantly harder problem to denoise multiple tokens, especially in the beginning. But it's much easier in the end because once you fill in these 3, it's much easier to predict these 2 at the same time for the denoiser. Yeah.
Yeah.
How do you deal with variable? Excuse me. How do you deal with variable sequence lengths? Like if you don't know in advance how long your generation is going to be.
Yeah, that's a very good that's a very major limitation for the current diffusion model. So the way I see people try to circumvent this is by either using the block diffusion method, like you can do block generation. So you can assume, I guess in this paper, that you can generate block by block and continue so the block are generated autoregressively. So you can continue generate until you think it's the end, and the last block is an empty block. Yeah, so that's how. Yeah, like I guess that's also one of the major limitation why autoregressive model like it's significantly more easier to just scale up to longer generation or arbitrary length generation for solving a problem. Yeah, compared to this kind of framework. Yeah.
And maybe you can give an overview. How are people approaching the like multiple tokens at a time diffusion? That seems like interesting.
Yeah. So the limitation like of the current transformer, right, is we can only predict the conditional probability of given that we have generated some tokens, we can only predict for each of the like the mass tokens we want to fill in. We're only predicting the conditional probability. So if we take the product of these conditional probability, they don't equal to the joint probability of tokens, should appear together. So that's a major bottleneck. But turns out this assumption like becomes easier to be like validated if you can do this in a later stage of generation. For image case, I guess that's a better example. Like once you have generated like 50% of all the tokens for this cat, you can pretty much fill in the rest tokens because you already know like they're pretty deterministic. You have to generate in that way to be consistent, right? So that's how I think that like the parallel decoding, you always start with smaller step sizes, like decode 1 token or 2 token at a time in the beginning, and then start to decode more tokens at later steps in the more like
And have you seen what do the vibes kind of look like for text in that sense? Is it like it plugs in a bunch of A's and thes randomly and then kind of fills in useful like concrete details, or does it tend to generate some keywords and then fill out answers, or just kind of like what do you typically see? Like how does that process usually go, just subjectively?
Yeah, for text, I think the current like diffusion methods they tend to like generate texts that are locally coherent because of the way you generate random sparse words at random places and in the long context in the sequence like 10, 12, 24. And then you start to like build local blocks of consistent text around those, but you are not able to actually generate a fully coherent block of text due to the reason why like you are generating pretty randomly. But also like that's a limitation of like the smaller models as well, like not being able to attend to like very far away tokens. So for multiple token generation, I think it's similar to the image where if you have generated most of the text, it will be easier for you to like fill in more tokens at once. Yeah, but I haven't really seen a paper that does this systematically. And the Inception Lab model seems to actually try to do this. That's why they are being able to generate so super fast. But maybe there could be like distillation you can do by first learning to generate token by token, but then try to distill from that. Yeah.
I have a quick question. I'm not too familiar with, I don't have a strong background on diffusion models, but I'm curious if your idea on using a planner would extend to like continuous diffusion for text. I think I've seen people use diffusion in the embedding space.
Yeah, that's a great question. So we have thought about this idea for continuous diffusion. So I think the most natural extension is like we can use a planner to recalibrate the time we're at for the continuous diffusion, and then try to just set the time back if we're not successful. So that's like a kind of like a test time inference method. You can do that, but in practice, like a lot of the benchmarks, the current like diffusion models already work pretty well for those cases. So you don't like have to set the time back for most of the case. But also there are cases where you generate something that starts to look awkward, like those like 5-leg chairs or 6-finger hands. You have to actually go back very far to regenerate a correct image. So the current recalibration method, you have to really train online for the verifier or the planner to know where to go back to. Yeah, so the training distribution of just perturbing the original data doesn't give you the signal for knowing where to go back. Yeah.
Got it. Okay, makes sense. So in continuous diffusion, you expect these rare kind of high failure modes, and this is where the planner would help the most.
Yeah, but it's not in a way that the planner can pick, where do I generate first. So it's like, the current diffusion models for image, they're not generating parts first. They are generating at the same time. So there's that part is like not not applies to the continuous like data problem. Yeah.
Makes sense. Thank you.
Sure.
What's the biggest diffusion model you've trained?
Yeah, in my case, I think the size is only 300 million. Parameter is pretty small. Like it definitely has like limitations in generation, like the problem I discussed. Like they generate random, sparse, coherent local blocks of text, but they don't make sense holistically. I think that's a problem with the model size as well. Yeah.
Do you know how it scales when you scale up?
I haven't really tried scaling up the denoiser part. Yeah. In this work, I mostly just only try to see if we change the sampling to this kind of sampling, what changes for smaller models. Yeah.
What's the biggest that anyone has trained?
Yeah, so the most recent work they trained, at least like in academia, they trained a 7 billion or 8 billion diffusion language model. And it seems like on some benchmarks, they are on par with the Llama 3. Yeah, I don't know how, so I think, yeah, like this method, this paper, they train like a 7 to 8 billion parameter diffusion. This paper starts from an autoregressive model like Lagrange 3 and then try to continue train. Yeah. I'm not sure about the size of the Inception Labs, which is commercial. Yeah.
Cool. If there are no more questions, Brennan, how do we wrap up?
Yeah, I think let's just go ahead and thank Sulin for his time. And Sulin, I'll be in touch with once I have a decision for you.
Yeah, thank you so much.
Thanks, everyone.
Thank you.
Bye.
Yeah, thank you. Thanks for the invite. Bye.
Bye.